Now we are going to learn how to derive the expression for excess pressure inside the air bubble. Already in the previous video, in the previous topic, already we have seen that excess pressure that is acting in the concave surface. Are you clear? I will explain how the excess pressure it is acting within the air bubble. Here, this is the complete structure of the air bubble within the liquid. Whenever you blow the air through the liquid, air bubbles will be formed. So the air bubble is usually it is surrounded by liquid. Here, for our derivation purpose, the air bubble that is split into two hemispheres. So here we have taken one of the hemispheres. So before going to derive, we have to understand how many number of forces are acting in the air bubble. Are you clear? Here there is a pressure. That pressure can be called as P1. The pressure which is acting from inside, it is called as P1. There is another pressure that is acting towards downward direction, that is acting on the surface. So one pressure is acting from inside, another pressure is acting from outside. And the most important thing is always the excess pressure. Excess pressure means difference between these two pressure is called excess pressure. That excess pressure will be acting only in the concave surface. Therefore, del P, what is del P? Del P means excess pressure that is acting only on the concave surface. That you should not forget. So it shows that P1 is dominating and P2 is less. So excess pressure can be written as del P can be written as, since del P is acting in this direction and P1 must be greater than P2. Therefore, P1 minus P2, the difference that gives you excess pressure. So both P1 and del P both are acting in the same direction and P2 is acting on the surface that is from outside. So here, this expression, excess pressure expression to be derived, that is our aim. And one more thing is, here let us imagine a molecule. That molecule, it is pulled by two forces here due to surface tension. If it is extended for the molecule which are present in the rim, so these are all the molecules which are present on the circumference of the rim of the air bubble. Okay, these are all the molecules which are present located on the rim of the air bubble. So on each molecule, what will happen? The force due to surface tension, they are acting in the downward direction, because if the lines are extended for other molecules also, the tangential force, they are acting on either side. If the same lines are extended here, so these are all the direction of the force due to surface tension. So on each molecule, the force due to surface tension that is acting towards downward direction. Are you clear? So these are all the forces which are acting towards downward direction. All are due to the surface tension. So these are all the forces which are acting on each molecule due to surface tension. And here the air bubble, its radius can be taken as R. Its radius can be taken as capital R. Are you clear? Now we are going to see how many number of forces are acting on the air bubble. How many number of forces which are acting on air bubble. That is our next aim. Here, look at here, one pressure is acting in the inside. Are you clear? P1 is acting inside. So one force is due to P1. One force is due to P1. Are you clear? That is acting from inside. Are you clear? That one will be equal to the sum of other two forces. What are the other forces? Another force is due to P2. Another force is due to P2, and it can be written as Fp2. That is acting towards downward direction, that is on the surface. In the same direction of P2, which one is acting? The force due to surface tension is acting. Therefore, Ft can be written. So, totally 3 forces are acting. One force is acting from inside, that is Fp1, and another one is FP2. What is FP2? Force due to pressure P2 that is acting on the surface, that is from outside. FT. What is FT? These are all the forces which are acting towards downward direction, that is due to force due to surface tension. So like this we have to write. Are you clear? So both are equal. Now the thing is, our next aim is force due to this pressure to be calculated. We know the general formula, pressure is equal to force per area. Therefore, force is equal to pressure into area. Are you clear? Force is equal to pressure into, here area means which area? This lower part of the hemisphere, one cross-sectional area is there, no? That area of cross-section can be written as, since it is in the form of circle, we can write it as P into pi r square. So this is the formula from which we are able to get the expression for force due to pressure. So here force due to pressure P1 to be written. Use this formula. Instead of this, we can write, since the pressure is named as P1, P1 pi r square can be written. This is the force due to pressure P2. Therefore, P2 pi into r square can be written. Force due to surface tension. For that, we have to get the expression. In the beginning of the lesson itself, we have learnt that surface tension is equal to force per unit length. This is a fundamental formula. Surface tension expression T is equal to force per unit length. Therefore, force due to surface tension can be written as T into L. T into L can be written. Here, length. Length means the length of the rim on which the molecules are present. Each one of them, they are pulled towards downward direction due to surface tension. No, the total length of the rim to be taken, total length of the circumference to be taken. Therefore, F is equal to T into surface tension into length is nothing but circumference. What is the circumference of the circle? 2 pi r we can write. What is the formula? 2 pi r instead of L can be written. Any doubt in this? And very important thing is, in the case of air bubble, only one free surface is there. So this is the only free surface which does not have any contact with anything that is inside. So only one free surface is there. Therefore, here 1 must be written. Here number 1 can be written. If any two surfaces are there we have tried 2. Since only one free surface on which force due to surface tension is acting, therefore 1 must be written, don't forget. Now force due to surface tension formula is ready. Instead of that, T into 2 pi r can be written. Are you clear? So this is the formula. Now what we have to do, bring this factor in this side, P1 pi r square minus P2 pi r square is equal to T into 2 pi r can be written. Here P1 minus P2 can be written within the bracket. Common factor is pi r square, which is equal to T into 2 pi r can be written. Any doubt in this? Now 1 r can be cancelled, pi can be cancelled. So what is the remaining thing? This is the expression. P1 minus P2. Already I have told the difference between P1 and P2 is called excess pressure. That excess pressure will be always acting in the concave surface. So P1 minus P2, that one gives you excess pressure. Are you clear? Del P into R is equal to T into 2. So I need the expression for del P. So del P is equal to 2T by R is the expression. Are you clear? Del P is equal to 2T by R is the expression to calculate the excess pressure. This excess pressure that is always acting in this direction, that is towards the which surface? Concave surface. Are you clear? This excess pressure and force due to surface tension, both of them must be in equilibrium. That is very important. The purpose of learning excess pressure is how the bubble is in equilibrium condition. How the air bubble, it remains always in the same shape. how it is able to maintain the shape. How is it possible? As long as the excess pressure is, the force due to excess pressure is equal to force due to surface tension, the bubble will be remaining in the form of spherical shape. Are you clear? That is the purpose of learning the excess pressure. Now this is a formula to calculate the excess pressure. By knowing surface tension and radius of the air bubble, which one can be calculated? Excess pressure can be calculated. Very interesting derivation. Okay, so now we have seen air bubble. Next we are going to pass on to the liquid drop. So clear, excess pressure in the case of liquid drop, its expression to be derived. Okay, so don't forget this expression. Okay. Now we are going to derive the excess pressure in the case of liquid drop. I didn't rub the board. I am using the same derivation which one was derived for the previous one, air bubble. Both are almost similar. The only thing is slightly, the assumption to be slightly changed. Here, let us imagine a liquid drop. The drop, it is fully made up of liquid and it is surrounded by air. Are you clear? Here, for the sake of the convenience, for the derivation purpose, the liquid drop is split into two hemispheres, as seen in the case of air bubble. Here, the inside part within which liquid is there, this is surrounded by air. Are you clear? As usual, the excess pressure is acting only on the concave surface. There is a pressure inside from the liquid side, that is P1. There is another pressure that is acting from outside, that is called P2. On each molecule of the liquid on the surface, the force due to surface tension is acting tangentially, and if the direction of the force are extended for other molecules, finally on the rim you can see plenty of molecule. On each one of them the force due to surface tension is acting, and the radius of the liquid drop can be taken as r. And here also, in the case of liquid drop also, only one free surface is there. Look at here, this is a free surface. So this is the surface which is having contact with air. That's why this is called free surface. Within which liquid is there? The inside, no free surface is there. The only free surface available only here, that is in the outside. Are you clear? So on the basis of the same assumption, I have derived. Again, I'll explain. Here, the force P1, force due to P1, that is acting from inside, that is from liquid side, and Fp2, this is the force due to P2, that is acting from outside, that is from air side, and Ft, what is Ft? This is the force due to surface tension. And already we have derived the formula for force due to pressure, P into pi r square. Same expression is used. Since it is P1, we can write P1. Since the force due to pressure P2, instead of that we can write P2 pi r square. Force due to surface tension can be written as T into 2 pi r. Only one free surface is there. Since only one free surface is there, what we have to write? We have to write 1. Don't forget, since only one free surface is there in the case of liquid drop, 1 must be written, and this P1 and P2 can be written within the bracket. Pi r square can be written outside, and T into 2 pi r, same expression must be written. Cancel the factors pi and pi, and 1 r can be cancelled. After simplification, the excess pressure derivation, that expression can be obtained finally. Therefore, del P is equal to 2T by R. The same expression was already derived in the case of air bubble. Are you clear? Now, the same expression is derived even in the case of liquid drop. So very simple one. That's why I didn't rub the board again. I have used the same expression as seen in the case of air bubble. For both liquid drop and air bubble, the excess pressure expression is del P is equal to 2T by R. Don't forget the term 2. Here, the force due to excess pressure and force due to surface tension, both are acting in the opposite direction. Both of them will be in equilibrium. Because of that liquid drop always it will be remaining in the spherical shape. That is the purpose of learning the thing. Force due to excess pressure and force due to surface tension, both of them are balancing with one another. They will be in equilibrium. because of that equilibrium condition, what happens? That liquid drop, that one will be always remaining in which condition? The spherical shape. Understood? Let's go to the next one called soap bubble. That is a special case. What is the next one? Soap bubble to be seen. Thank you. Okay. Finally, we are going to derive the expression for excess pressure in the case of inside the soap bubble. Already we have derived the excess pressure inside the air bubble as well as in the case of liquid drop. Now we are going to see the final case, that is soap bubble, within which excess pressure is acting. For that we have to derive the expression. Look at here how the soap bubble will be. You may have seen the soap bubble. Within the soap bubble, nothing is there. Vacuum is there. Are you clear? No material medium, no liquid, even air won't be there. That region is vacuum. Outside the air bubble, air is there. Are you clear? So that is a nature of the structure of the soap bubble. In the case of soap bubble, how many free surfaces are there? Look at here. Within this vacuum is there, so there will be a free surface, and another surface is there outside, that is in contact with air. One surface is in contact with vacuum, another surface is in contact with air. Therefore, how many free surfaces are there? 1 plus 1. Therefore, 2 free surfaces are available in the case of soap bubble. Are you clear? Now, as usual, the same kind of treatment to be done for derivation. That soap bubble that is to be split into two hemispheres. So these are all the molecules. These are all the liquid molecule which are present on the surface. On each molecule, the tangential force due to surface tension is acting. If other molecules are considered, these are all the directions of the force due to surface tension. So here, the remaining molecules, they are present on the rim of the circumference of the soap bubble. Are you clear? If you cut the soap bubble into two, in the middle part, the circumference area, the lower part of the hemisphere, large number of molecules are there. On each one of them, the force are acting due to surface tension. They are all acting towards downward direction. They are all tangential forces. Are you clear? The force due to surface tension to be calculated. How to calculate the force due to surface tension? T is equal to F by L. Surface tension is equal to force by L. F is equal to T into L. So force due to surface tension is T, surface tension into length. Here, how many free surfaces are there? 2. Therefore, the force are acting on two surfaces. Therefore, 2 must be written. 2 into T into, instead of L, the circumference to be taken into account. How much? 2 pi R. So this is the circumference. So this is the force due to surface tension. Now, in this expression, instead of force due to surface tension, what must be written? 2 into T into 2 pi R must be written. Are you clear? Already we know the expressions for force due to pressure P1, force due to pressure P2. Here also the pressure P1, it is acting from inside and P2 is acting from outside. The force due to pressure P1 and force due to pressure P2, all those derivations were already taught, all are written here. Are you clear? And then all the factors are brought in this side. Now this is the only factor that is left out in the RHS side. So 2 into 2, 4, are you clear? T, pi, R. So this is the factor which is available on the other side. Here the excess pressure can be calculated from this expression, P1 minus P2 pi R square is equal to 4T pi R. That is the expression. Pi can be cancelled, 1 R can be cancelled. P1 minus P2 is nothing but excess pressure that is acting from inside, that is on the concave surface. Don't forget, excess pressure del P will be always acting on the concave side. That concept should not be forgotten. So therefore, P1 minus P2 can be written as excess pressure. Are you clear? This R that can be taken on the other side. Therefore, the expression that one becomes 4T by R. So this is the expression for excess pressure which is acting inside the soap bubble. Only in the case of soap bubble 4T by R expression can be observed because two free surfaces are there. That's why in the final expression you could see the number 4. In the case of liquid drop, in the case of air bubble, del P is 2T by R. So be thorough with all expressions. Are you clear? So to remain the soap bubble in the form of spherical shape, how many forces are required? One is force due to excess pressure and force due to surface tension. Both are acting in the opposite direction. Both of them must be in equilibrium. Only then the soap bubble will be remaining in spherical shape. That is another concept. So this is the expression for excess pressure. Okay. So I have derived the excess pressure in the case of soap bubble, excess pressure in the case of liquid drop, and also in the case of air bubble. Okay. Be thorough with all the expressions. Okay.